Next, let's utilize the buck converter as the example to show you how can we utilize the first harmonic approximation method to build the time domain model for the circuit. So we are going to first talk about the generalization and FHA here. So the word generalization, generalized, refer to this generalization. So in this section, we are going to disclose how can we generalize the power converter circuit. So first, let's plot the schematic of a typical buck topology. So here is the input source. And we have a switch network composed by a MOSFET Q and diode D. On the right-hand side, we have the filter network with L, C, and load resistor R. So here is output voltage. Before we talk about the mathematical analysis, we also first need to define the directions of currents and polarity of voltage. So we care about the inductor current, right? Here is positive IL. And also care about its voltage. So we define here is positive polarity, VL. And here we define this as positive capacitor current, IC. So we first have an overview of the two operation modes for buck in CCM. They are mode 1, which correspond to the time from 0 to DTS. In mode 1, we know that the Q is on, D is off. So we can write the expression for inductor current and capacitor voltage. As we mentioned earlier, usually we use those two quantities as the state variables, right? So for the inductor voltage, the DIL over dt equals to 1 over L times the voltage across it, which is the difference between the input voltage and output voltage. And the second equation is the capacitor current equation, right? So dVO over dt equals to 1 over C times the capacitor current, which can be analyzed based on KCL in this note, which is the difference of the inductor current and load current minus and next, let's look at the similar group of equations in operation mode 2. Which occurs from DTS to TS. In mode 2, we have the Q off. And the diode will continue to follow the inductor current. Diode will be on. So we write those two equations correspondingly. The first one is the inductor voltage equation, DIL over dt equals to 1 over L. Right? Think about the case D is conducting, so the voltage across it equals to minus output voltage. For the second equation, capacitor current equation, dVO over dt equals to 1 over C, which is unchanged, right? Still, the difference between the inductor current and the load current. Then here comes the question. How can we generalize the expression of the two operation modes using one set of equations? We got inspired by a tool, right, which we can introduce a commutation function. So 3, we can introduce a commutation function. So we use a ut to work as the commutation function. So ut is like a step function, so which equals to 1 at the range of mode 1, right, from 0 to dts. And ut equals to 0 for the range in mode 2, which corresponds to dts to ts. We can graphically plot the waveform for ut. Ut is also a periodical function. In time domain, so here's ut. Here is the one switching period, ts. And here's the boundary between mode 1 and mode 2. So ut should have a kind of square wave feature like this. In mode 1, it equals to 1. Mode 2, it equals to 0. Then next switching period equals to 1 again. So by introducing such a commutation function, we can combine those equations together to generalize the circuit function. So step 4, we generalize the circuit function. So first, look at this pair of function, right? Basically, it's like we multiply V in by ut, so we can combine them together. VO part is remain the same, right? So we'll have the first function as dI L over dt equals to 1 over L V in times ut. Minus VO. So one equation describes the two states, right? Only by introducing a periodical commutation function, which is very, very smart. And next one is this one, the capacitor equation. So dVO over dt equals to, look, they are unchanged, right? So we don't even need to introduce ut, just as it is, IL minus VO over R divided by C. Okay, next we can process those two state signals, right? IL and VC. We can implement the FHA, right? First, the harmonic. Approximation. Meaning that we expand those periodic signals into 3 terms, right? K equals to -1, 0, and 1, right? For example, the inductor current is approximately equals to the sum of 3 items. First one is IL minus 1 T E2 minus J omega T. And second one, IL0 t. This one equals to unity. Third one is IL plus 1 t e to j omega t. Similarly, we can do the same thing to the capacitor voltage, which is also a periodical signal. Expand the capacitor voltage with FHA. So VCT equals to the sum of VC minus 1 VO E2 minus J omega T plus VO K equals to 0 T plus VO K equals to plus 1 T E2 J omega T. So note that they are both equal to the sum of three series. For each series, it has a Fourier-like coefficient. This coefficient, as we mentioned earlier, it is a complex coefficient. So we can use a complex notations to those 6 coefficients. So we can assume that, for example, the IL0 for k equals to 0 is a little bit special. If k equals 0, we no longer have the imaginary parts. So it should be a real number. So we just refer to this to a quantity as x1. And similarly for VO, k equals to 0, we refer this to x2. x1 and x2 are both real numbers. And for the k equals to 1, right, positive 1, for IL's Fourier coefficients with k equals to plus 1, this is a complex number, right? So this will be x3 plus jx4. And meanwhile, for the k equals to minus 1, based on the definition of the Fourier coefficients operator, so k equals minus 1 should be equal to the conjugate of the k equals plus 1, right? So this will be x3 plus minus jx4. And the next one is the VO plus 1. This is also a complex number. We introduce x5 and x6 to denote it. So x5 plus jx6. x5 is this complex number's real part. x6 is the coefficient of its imaginary part. So the VO minus 1 equals to its conjugate minus jx6. Then we insert those representations of the Fourier coefficients into the IL and the VO correspondingly. First, we look at IL. So equals to, here we replace by x3 by plus jx4 e2 minus j omega t plus this quantity is IL0, which is x1. And this quantity is IL plus 1, which is, here is minus 1, right? Minus 1. So x3 minus jx4. So here is plus 1. So x3 plus jx4 e2 j omega t. Then we can rearrange this equation by extracting the x3 and x4 terms separately. So this should be equals to x3 e2 minus j omega t plus e2 j omega t plus x1 plus x4 e2 j omega t minus e2 minus j omega t. So when we see those terms, right, if you have ever taken the calculus class, you should be reminded of the one very important formula. We call it the Euler formula, right? Euler formula tells us that the cosine and the sine can be decomposed by the sum of two exponential terms. So like cosine alpha equals to e2 j alpha plus e2 minus j alpha divided by 2. And sine alpha equals to e2 j alpha minus e2 minus j alpha divided by 2j. So comparing those two representations, we can easily see that this can be replaced by cosine item. This can be replaced by the sine item, right? So therefore, the ILT can be simplified as 2x3 cosine alpha refer to omega t here. This one minus 2x4 sine omega t. And the x1 is as it is. And similarly, we can also analyze the capacitor voltage signal, right? So the VOT equals to, we insert those quantities, VO minus, right, to here, and VO plus to here, and combining them. So I will write it, the combined result. We will have x5 term, extract x5's coefficients and put it together. So E2 minus j omega t plus E2 j omega t. And for the x6 terms, we also combine them together. So here is like minus 2x6 times E2 j omega t minus E2 minus j omega t. And this one, VOT, k equals to 0, have its value equals to x2. So x2 as it is. And again, we utilize Euler's formula to simplify this expression. We will obtain that VOT equals to 2x5 cosine omega t minus 2x6 sine omega t plus x2. Okay, so till now we have derived the expression for XLT and VOT separately. So those two equations tells us that XLT and VOT are kind of periodical signal with the angular frequency equals omega, right? And if we want to solve their time domain model, we just need to solve the values for from x1, x2, x3, x4, 5, 6, right? Then we can fully obtain the time domain model for the state variables in the buck converter. Okay, so in this section, we have introduced the commutation function to generalize the two models of the buck converter. And also we did the first harmonic approximation for the state variables, including inductor current and the capacitor voltage. And combining the Euler's formula, we can further simplify the expression for the inductor current and the capacitor voltage.